Okay, thank you very much for attending this session. My name is Rafael San Miguel. I come from British Telecom. And please let me introduce you to Rafael Villoria, who comes from Nestle. Today we are going to spend some time on describing the design and implementation of the security analytics platform that we are building at Nestle. But before that, we wanted to give you some background on what Nestle is.
So just a bit of context to start and a motivation also for the project. So obviously, many of you may know Nestle, maybe you know, maybe you don't. It's also a big company, obviously a worldwide company, many brands, many global brands, many local brands, different type of businesses from selling to trade to e-commerce like Nespresso, Dolce Gusto. Many employees, as you can see, more than 300,000, located in all countries around the world, with factories, with sales head offices, etc. And obviously, as you can see, I mean, probably you have enjoyed some of the products, or either yourself or maybe your pet, possibly. So maybe you want to highlight something.
We are going to explain the security analytics concept from two different approaches. And we will be explaining why big data was a key element for us. And as I said, we are going to take two different approaches. So we have decided to put these kind of pictures, these so-called optical effects, because you can see two things in the same picture. So this is just to remind you that we are using two approaches for cybersecurity, and one of them is big data. We have also included pictures just in case you don't like the presentation, so that you can at least keep yourself entertained. So we challenge you to find both pictures in each of the images that we will be showing.
So basically a bit the motivation as well, no? So probably you are aware of that, no? That's somehow an impacting number. That's 700 million data records lost or stolen in 2015. And so 2016, we don't know yet, but trend shows, I mean, we don't need too much of analytical capabilities to see that the trend goes up, no? So that's happening, and we see hacking and malware, key elements, key topics, key drivers on this situation. So as you can imagine, companies like Nestle, that we also manage a lot of data, and we collect data from consumers and customers. We don't want that data to be stolen or to be leaked. 229. So 229. What 229 might be I don't know, many things, right? But in this case, that's actually something a bit scary as well. I mean, it's related to the median number of days that an attack happened to an entity, to a company in this case, before it's being detected. So during these 229 days, the breach happened already, and the companies realized 229 data. 63%. So 63% here relates to the number of companies that they learn about their breach from a third-party entity by another entity. So they were not realized by themselves. Obviously, that's not good either. No, that's also not something that the company wants to highlight when it needs to go on to the press and highlight these type of things. And wow, that's even worse. No, that's 100%. So 100% of the cases, what happened? That's even worse. It's basically something we know is that in 100% of the cases, the victims had their antivirus signatures up to date. So that kind of highlights a bit the situation, the context of what we need, something we need to do different from what we're doing to actually maybe try to avoid these issues. But we have some constraints. What happens is also that traditional cybersecurity has been built over real-time monitoring with the aim of detecting, sending all the logs in real time to what we call SIEM, to analyze, look for patterns, and then normally known patterns, and then highlight those so that then you can respond fast. What happened is that now anymore, the attack is not just one single way that will create a lot of noise, but it's actually a multi-stage, multi-vector attack that then a real-time engine is not prepared to identify, because you may see something at some point in time which is not so significant, so the analyst may not consider it critical. A few days later, you have something else happening, and obviously these systems are not there to relate those dots, so you will not see this type of attack. Then is the reliance on signatures, and we highlighted that before with the 100% element. No? So traditional security also is based on signatures, and yes, this is good. It stops a lot of noise around, but then the real attack is not going to be detected. And it's also for malware very simple, because obviously many of these signatures are based on hashes, but as soon as you change a few lines of code, the hash is different, and so they can attack with something different, and the antivirus will not know. And by the time it's updated, you have been breached already, or you have been attacked. And then the other thing is excessive time to the inside. So this amount of data that you are also ingesting into your real-time engines, when you have an incident, you want to do investigations, you do hunting, then you realize that your queries take a week to actually complete. So, so that makes for the analyst also very difficult to work on, because obviously you don't know the query, the good query you don't know just at the right time. No? So you are trying, you do trial and error. So you need those systems to give you the answer very fast, so that you can find out, you can start looking for things. So that's actually what we traditionally are having in place, and which are not allowing us to actually be much better than the attackers.
Okay, and we wanted to give you just a few examples of how this real-time monitoring works. So in the first example, we have an event that is called multiple failed logons. So we see that in the management console. And what it means, it can mean that someone is brute forcing the account, so he's trying to break in, and that's going to be 100% of the time. And 99% of the time, it's going to be someone coming back from holidays. He doesn't remember his password. So 99% against 1%. Imagine how much work is involved in coming up with the 1%. We have another one, reconnaissance activity from the internet. This can be someone that is preparing an attack, and prior to that attack, he is doing reconnaissance. He is trying to investigate about the network assets. Or 99% of the time will be false positives, or someone that is scanning the network but will never launch an attack. And the last one is critical SAP transaction executed. It can be the last step of a cyber attack, of a complex cyber attack. 99% of the time, it will be someone that is simply doing his job, and he needs to execute that transaction. So here, I think that you can see the challenge. But there is even more, because the attacker, if he has got the password, somehow he will not fail the logon. So you will never see multiple failed logons. It can happen that the attack will occur without any reconnaissance, so you will not see the second event. And finally, it might happen that the attacker doesn't need a critical transaction for the attack to succeed. And then we don't see the last event. So that's how blind we are, and that's why we need to make something about it, right? Okay, so in our environment, what we have is 6 billion security events generated every week. That is about 30,000 events per second. That is coming from 250,000 employees across the globe, right? And we have two different approaches, as we said. We have the firefighters that are the guys in charge of the real-time monitoring. So in this case, what we are doing is we are using correlation rules with common intrusion scenarios. So we know that this is an attack, and so we will be detecting it in real time. The goal here is always to respond fast, and we don't have a lot of time to think. To think, we have something else, which is the lab, right, with the scientist. And what we have here is a data lake where we identify complex attacks, where we identify attacks that cannot be defined by a specific pattern. In this case, the goal, again, is to identify everything that hasn't been caught by the firefighters. There is something interesting here, the kill chain. The kill chain are the steps that an attacker follows to execute an attack. And it is a very important concept in our case, because we need to define what is a cyber attack. And we cannot fall into the mistake of defining it in terms of known intrusion scenarios. So we need to be more generic, because otherwise we will have the same problems that we are facing now. And so we define a cyber attack as activity that is different from legitimate activity, and we also assume that most of the activity is going to be legitimate. So what we need to detect are anomalies, right? Things that are different from regular activity. And those things that are different can be thought of as evidences, as traces that the attacker is leaving as he is executing an attack. But we have to keep in mind that those anomalies will not be an attack in itself. They will be just traces, and we need to connect the dots if we want to come up with the actual attack. Okay, so what information are we getting? We are getting user authentication that is coming from Microsoft and the VPN. Internet browsing that we are getting from the content filtering proxy. We are looking at network connections from the firewall and the IPS. SAP transactions, because it's all about business, right? And business is happening in SAP. We also look at the server behavior, mainly Microsoft. We are gathering threat intelligence, both from open source intelligence and also vendors. We also see the web traffic, and we see the internet domains that users are visiting. So that's the information that we have. It looks very rich. It looks like, yeah, a paradise for a data scientist, right? Having all that information. But then we have something to keep in mind as well. For each of those log sources, we have thousands of event types, especially for Microsoft. And we have things like, okay, so for servers and domain controllers, we get things like a computer account was changed, a service terminated unexpectedly. From the intrusion prevention system, we get things like cross-site scripting, or things like content protection violation, and things like that, right? And from the content filtering proxy, we get things like this access to this website is allowed, or it is not allowed for this reason. And that's all we get. So my question to you in this case is, how will you be using that in a regression model or a classifier, or how will you be using that in neural networks, right? So we need to do something about it. We need to transform that. And one of the things that I noticed when I joined the project, I wanted to keep on playing with my petal and sepal length data set that was so nice to create clusters. But then I had this information, just the log source, the target, the username, error code. So this was not so fun. And at the end of the day, the iris data set looked like a white unicorn in my environment. So we need to define an architecture. We have to also point out that the architecture is always work in progress because there are so many things coming in, and we need to adjust to new requirements. But we try to keep it as stable as possible. I will start by highlighting the technology stack. This is what we are using. We are using Microsoft Azure environment. We are using HD Insight with Hadoop and Spark. We are using R, and so we are using R Studio. And we are also using RiboScale R, which is not so well known. Those are the big data libraries supplied by R. And we are also using Spark R. For visualization, we are using Kibana, especially for data exploration, Power BI for the final results, and Tableau for the analyst.
Yeah, so I mean, one thing that is quite important maybe to highlight, and that took time also to analyze, is the need of looking for a platform that allows to be very flexible, and that also allow us to actually fit new solutions, because what we see is that this is an environment that is moving very fast, and obviously in a corporation, you always look at having, I mean, there is always hesitance to go out cloud, you look at in the in-house, you look at having in the cloud, and there are pros and cons, but definitely what we saw is that one key element was to have one platform that would allow to have all the elements in the same platform so that we don't need to play around by moving data to one location and the other. And also that allows us the flexibility to one scale, and also to start adding new components, new technologies that are coming up into the environment that we can also plug in into the same environment. And especially the speed to put it in place. Also, obviously, even these type of things you start before, and then we realize also quickly that when we try to build a Hadoop cluster with R, etc., in-house, that will take 1 year. Well, if we do it in a platform like Azure or Amazon, whoever, one of those, in 24 hours, we had already everything started, no? So that we can focus on other elements and not just on buying the hardware, racket on the data center and all these kind of things. So that was really something that took time also to convince, let's say, senior management to go into this direction, but it's a key element to have in mind while deciding the technology stack and the platform to use in this type of scenarios.
Okay, so let's have a look at the building blocks. This is a pretty standard process, right? So we start with ingestion. We do transformation of data. When we do the transformation, then we come up with the actual data model that we can work with. Based on that data model, we can do the predictions, and then we visualize them. The predictions are the anomalies that we have detected. For the predictions to work, we need to do first data exploration. We need to understand data, and then we have to create models for that data that will be used for predictions, right? So pretty standard. But let's have a look at a little bit more detail on this life cycle. So we start with ingestion. We are gathering information from all those log sources. We do the batching with the CSV files. We send them through the internet, and we get them into Azure. In Azure, we are using Data Factory as the orchestration component. We are using blob storage. Blob has nothing to do with the Oracle data type. It is the way Microsoft calls this storage. And then we are using MRS, which is the Microsoft R server, connected with Spark and with RiboScale. With RiboScale, we can run MapReduce jobs, or we can run Spark jobs. And then we use Power BI for visualization. So what we do in the transformation phase, we said the raw data is something that we cannot use as it is, and we need to do something about it. So we take all those fields, and we translate them into things that we can use in models. For example, we are creating behavior records. So we are recording activity in such a way that it can be then used for calculations. We are creating metrics. We are creating ratios and time-based measures. And we are also incorporating information from external sources and information that we have about the network. And so we have a useful data set. Once we have the data ingested and transformed, we do the predictions, and we come up with the anomalies. And those anomalies are then visualized. And the visualization is something that we use for two things. One of them is for the analyst to actually handle the incidents, and also for management, which is actually a key component.
Yeah, I think also it's good to highlight here that, I mean, on these big projects, it's good to also look at in a different phases, and also trying to always be able to show the benefit of this project. Normally, these are big endeavors, so you don't want to sell something just and have people waiting for 2 years to see results. So what we are trying always to do is through visualization, that is the best way to show that, not to people who it's much maybe not too deep into the analytics, is so that they can understand, they can see what's the benefit of all the work that is being done behind, and not waiting for the super rock star analytic model that will give us the answer, but at least to have some visualization that already are providing some insights out of the data with maybe certain analytics that they have not seen before. But especially that allows to continuously show the progress and keep having the support, obviously, of the funding at the end. That's also an important element to continue with the project, no? And having that continuous improvement mindset, and so that they can see that already from 3 months we have something that we can deliver, and that it's not taking 2 years. I think that's quite of a key element to keep the thing going.
And with that in mind, we noticed that we needed to keep the hype high, right? So we needed to keep everyone interested on this. So as Rafael was saying, we couldn't wait too much, and we started by doing data exploration, and we created some models. So this is one of the exploration exercises that we did. For this, we are using Kibana, but we are also using R. We take samples of data, and then we try to make sense of them. And this is an interesting story because one of the things we were looking at based on user browsing behavior, we did a calculation. We calculated the distribution, the proportion of visits to each country from each user. So how many websites hosted in Spain, how many websites hosted in the US. And obviously, you can imagine for a multinational company, there were many clusters, but there was one cluster that was especially interesting because it didn't follow the pattern of any other country. So what we did was we did some visualizations. One of them was the one you see on the right. And that was the amount of connections of that particular cluster. That's a standard box plot. And you see that the number of connections is actually quite higher, quite bigger. What was the reason? We went to those workstations, and we noticed that those workstations had a spyware installed. And so every time a user visited a website, there was another request on the back of it being sent to a malicious server to inform that the user had visited that website. So it was basically recording the browsing history of every user. This is not a very complex analysis, but it took us to very good insights, right? So now we have one possibility. We have the possibility to identify systems that are compromised without signatures. So getting a little bit more on the models. So we are using 3 different strategies. One of them is behavior analytics. So we are basically comparing the current behavior with the one that was shown by that user or that IP in the past. To build this, we are using things like, because obviously we need to build clusters. We cannot compare a user alone. We need to compare it with a cluster. We are using things like Spearman correlation, Kendall, cosine similarity. We are also using graph analysis. For time-based, we are using Granger's causality test. Then we are using classifiers, all sorts of classifier, logistic regression, LDA, QDA, KNN. And then we are using multivariate outliers, because obviously we need to identify infrequent combinations of features. And for that, we are using Mahalanobis distance, high leverage points, Cook's distance, and so on. And then the bonus track is we are using scoring to combine all the anomalies that we detect and come up with a risk level. We are using supercorrelation and cascading algorithms, and this is something that we will explain a little bit later on. So let me put you a very concrete example of one use case. For user authentication, what we are doing is we built a matrix of users and servers to which they are authenticating. That is the matrix in the middle. So we are recording to which servers those users are somehow connected. And we are adding information about the behavior. So how this user is behaving every hour in terms of how many authentications. We also identify the behavior every day of the week. And we are also recording the source and target location of those authentications. So someone in Spain is authenticating in the UK, or in the US, or in Spain, whatever. And we record all that information, and we create clusters. So when we receive new data, a new user authentication, then we are able to tell whether this is compliant with the previous behavior, or if it is deviating from the previous behavior. And then we raise an alert. There is something that I always like to explain, because this doesn't look like very fancy algorithms. But it is important to notice that when we are dealing with such a big amount of data, we have to take like different approaches. The direct path is not the right choice. So for example, if we want to do a correlation matrix, when we have hundreds of thousands of users and 20,000 servers, this is not something that will fit in memory. So we need to do something else. We need to use RiboScale. In this case, it is just a simple replacement, but you have to think about it, right? This is not so straightforward. And also for clustering, you may think that you can use things like k-means, or you can use hierarchical clustering, but this is not the case. Because we don't know how many clusters in advance we can have, and this is not about guessing. It will never work for hundreds of thousands of users and thousands of servers. And so we need to use graph analysis to do that clustering. So those users or systems that are similar, then we create the graphs, and we see which graphs are connected, and then we have the clusters. So we need to work on workarounds to make things happen. The other use cases that we wanted to discuss with you is detecting the internet domains that are malicious, that are hosting malware. And for this, we use a classifier. We use, well, to be more specific, we use a principal component analysis. So we are taking a data set of malicious domains, and we are also taking a set of legitimate domains, and we are recording a number of features of those domains, and none of them have anything to do with security. In this case, what we are using is using marketing metrics, information about the HTML, so when we query the domain, what we get as a result, and CEO metrics. And this is what we are recording for each domain, and then we run the principal component analysis, and we paint that in a scatter plot, as you can see, and you will see that there are two different colors, and there are two different types of domains, the ones that fall above the line, and those are the legitimate domains, and malicious domains that fall under the line. And this is the training phase. When we send, and this is just testing, 4 malicious domains, you see that they get painted in the right side of the graph. So they fall behind, they fall under the curve, which means that they have been properly tagged as malicious. This is a test that we did. It worked very well, and actually you can see the article that we wrote in Data Science Central. When we tried to scale this to Nestle scale, we noticed that it was not working so well. And so we are now combining these features with additional features, for example, related to user behavior, how they are browsing those websites, to narrow down a little bit more and being able to identify very accurately those domains. But the power behind this use case is that as long as you have an acceptable accuracy, then you are able to identify malicious internet domains without any signatures. You don't need to know in advance that a domain is malicious for your systems to identify it. And finally, we have the supercorrelation concept, because we said that many of the anomalies that we are going to find are not going to be an attack by itself. So we need to connect the dots. We need to connect anomalies that might be a false positive or might be something very dangerous. And for that, we use the supercorrelation engine. What is it doing? Let's say that we have one user that has authenticated in one server, and that server has browsed one domain. And we have anomalies on each of those assets. Those anomalies alone might mean nothing. But if we connect the dots and we see the anomalies as a whole, then we can identify that perhaps someone has broken that computer, then he logged in maliciously in one server, and he did something to visit one malicious domain, perhaps to upload data that he has stolen. So then we can see the full picture, and we are not limited by the real-time monitoring that we were discussing before. We wanted to share with you not only the success, but also the pains, and we wanted to be very sincere on the difficulties that we are finding and how we are defeating them.
So yeah, I mean, one of the key elements also that we are also keep ourselves always looking at is a balance between complexity and simplicity in terms of finding always the model that really accurately identifies these things versus a simple model that gives us a reasonable accuracy. Because at the end of the day, I mean, there is a certain level where we are able to tolerate a couple of false positives, and we don't want to have too much complexity, because you may end up in some sort of overfitting. So there we have some examples where we elaborated and we got some challenges. So we always have to say, okay, let's go for simplicity. Let's always try to find out something that is simple and is good enough. And that integrates as well. No? One of the elements also is when you try to do it when you try to find the best solution, then you find out that actually when you try to kind of industrialize it, to put it in production, then it's too complex also to integrate from an end-to-end point of view. And that goes also for the algorithms, and it goes also for the type of data. And also the real data, also the real type of data at the end, also when you see it with volumes, doesn't really always show what we identify first with the samples. No? So that's also, again, another challenge, another pain somehow that we are trying to find out how to solve, is in terms of understanding better the type of data we have, and then make the algorithm that is resilient to also, let's say, changes on that type of data, because they're also, let's say, in this case, what we are looking for outliers, it happens that also there is legitimate outliers as well, and that's also the element that we found a bit more difficult to come across.
Yeah, if I had to summarize the pains and the lessons learned in 3 items, I will say first, the over-dispersion, right? So in one algorithm, you start working with a data frame, then you have to move it to a Spark data frame, then you roll it back to an R data frame, then you convert it to a data source, and the result is again in R, and you plug it into a CSV file or a Parquet file. Creativity, you have to be creative. The algorithms that you learn in the master program will not work, and you will have to find something else that will fit better. And finally, the data set, remember the IRIS data set will never be there, and you will have to go for creating features that will be useful, and you will spend a lot of time on building those features. And that's pretty much it. Thank you very much for your time. If you want to keep in touch, you have my email address there. Remember, while we are here, we have all those attacks, all those breaches, all those people breaking in. And that is the aim, and that is the reason why we will keep on working on this project. So thank you very much, everyone.
Thank you.